So your first example, we want to talk about the continuity of this. So we're going to actually talk a lot about this function. First of all, it's a rational function. Okay. And let's see all what we know. Well, first of all, always factor rational functions. So this is what it factors to, and you can't cross anything off. But this tells you a whole lot. First of all, it tells you that you have vertical asymptotes here at 0 and -1, wherever the denominator equals 0. So I have vertical asymptotes at x equals 0 and x equals -1. And how do I know about 0 asymptotes? The limit does not exist. So if you had to prove it, you'd have to say the limit as x goes to 0 doesn't exist. And the limit as x goes to -1 doesn't exist. Okay, so you know it has vertical asymptotes at x equals 0 and x equals -1. You know it has a 0 at x equals 1 because you put this equal to 0, so you would only have the numerator. So you know it has a 0. You also can talk about the horizontal asymptotes, which is the end behavior. It's your infinity limits. So how would you do that? Well, it looks like we have x. You can look over here. The degree on the bottom, so for horizontal asymptotes, this is pre-cal stuff. The degree on the bottom is greater. So y equals 0 is your horizontal asymptote. So if I'm looking at this graph, okay, I have a graph now where I have a vertical asymptote at 0, a vertical asymptote at x equals 1, a horizontal asymptote at y equals 0. And now remember, the horizontal asymptotes you can cross. So then it might ask you like whether it's the discontinuity, what kinds of discontinuity would it be at 0 and 1? So they would both be infinite, right? Because they're asymptotes. So that's infinite discontinuity. You don't have any holes or jumps, so you just have two places where it's discontinuous. So if you were to graph it, it would be like this, and then this one comes and it has a 0 at 1, but then it comes back and follows that, and this one is like that. So it's sort of a weird graph. But really, all they would ask you probably is about vertical or horizontal asymptotes, or about what kinds of discontinuity. So it would be infinite discontinuity at x equals 0 and x equals 1. All right, let's go on to example 2. It says, discuss the continuity of f. All right, so the continuity. All right, let's just start at the very leftmost side. It has continuity. You can have left-sided and right-sided if you're at an endpoint. So this has right-sided continuity at x equals 0. It has left-sided continuity at x equals 5. So those are your endpoints taken care of. Then we look at this area right here. We have what's called removable discontinuity. That's because you have a hole and then it's filled in somewhere else. Okay, and it's removable because if you reassigned this point right here, this 1, 0, and set it equaled that, then you could you would no longer have a discontinuity. So that's why it's called removable discontinuity. That's at x equal 1. And then this discontinuity is called jump. So you can see the graph stops and then starts up higher. And so it's not like just a hole. So that's called jump discontinuity. Okay, so infinite and jump are not removable or non-removable. Sometimes it goes, which ones are non-removable? All right, that's example 2. And let's do one more. So Number 3 says, is f of x equals 1/2 x to the 4th minus the square root of 3x squared plus 7 continuous at x equals -1? Well, the answer is yes, most definitely. Why? Because this thing right here is a polynomial. And, oh, there's my cat crying. All polynomials are continuous. So it doesn't matter where you asked, it would be continuous. All right, I'll stop the video there.